Hello, welcome to another module of this course, analog circuits. So, in the past module, in the last module, we had covered Nyquist plot and how to determine stability of a system from the Nyquist plot. But then the Nyquist plot is a frequency domain technique for determining whether a system is stable or not. What I mean is that only when you know how the open loop transfer function behaves for various frequencies, you can understand or determine whether the system is stable or not from the Nyquist plot. Now, there is another method for determining whether the system is stable or not, and that is from the roots of the characteristic equation. So, in this module, first we will cover what kind of response we can expect depending on the various root positions, depending on the various positions that the roots of the characteristic equation can take. So, recall what we mean by characteristic equation. We had covered a few modules back, in fact in the first module actually, when we were discussing the transfer function. So, characteristic equation, recall that if we have a transfer function of this form, a numerator polynomial and a denominator polynomial, then this denominator polynomial is known as the characteristic equation. So, ds equal to 0 if I set, then this is known as the characteristic equation, and the roots of these characteristic equation are also known as eigenvalues or poles. In general, the root of a characteristic equation, the roots of the characteristic equation will have the form like this. The roots or the poles can be written like this. That is, if the coefficients of the characteristic polynomial is real, then all the roots will be either real, or if they are complex, then they will be in conjugate pairs. Now, suppose the root is of this form, then the output that we can expect will be of this form. And this comes out to now, if sigma 0 is positive, that is, poles are located in the right half of S plane, then what happens? Then, from what we had discussed earlier, that if the poles are on the right half of the S plane, then what we can see from this equation is that if sigma 0 is positive, then as time increases, this value increases exponentially, and therefore, the output will keep on increasing exponentially. Hence, that is a unstable. So, it will be, as we had discussed earlier, it will be something like this. So, there will be oscillation. This is the envelope of the output, and the output will be something like this. So, the frequency will remain same. Actually, here from it appears as if the frequency is decreasing as the time progresses. No, the frequency remains the same, which is omega n, but this envelope, as you can see, the amplitude of oscillation gradually goes on increasing. So, this will be your this envelope, upper envelope will follow this line, and the lower envelope will follow this line. If on the other hand sigma 0 is negative, then what happens? This implies that poles are in the left half of S plane. And then from the equation that we derived earlier, this equation, if sigma 0 is negative, then you can see that as time increases, this response will decay, and finally for a very large time interval the output will be negligible, not 0, but negligible. So, what does that mean actually? What it means is that the response is bounded. Now, what does this word bounded mean? Bounded means suppose this is your input, sorry, this is T, this is say V in T, you introduce an input like this. Okay. Now, see, this input is bounded. Why? Because it does not continue. Say this is T1 and this is T2. It exists only between T1 and T2. After T2, it no longer exists. So, for a stable system, what we need is that the output, okay, which will start somewhere after T1. So, this is my say VOT, the output voltage of some system. So, this is the input voltage, this is the output voltage. It starts somewhere, but it should not go on expanding like this, it should fall. Okay. So, the expected response should be like this. It need not be at T2 that it becomes 0 suddenly, it need not follow the input closely, but it should fall after some time. So, this should not happen, this part should not be like this, it should go up and go down. Now, this kind of system is called bounded input, bounded output system, and this is one of the characteristics of a stable system, that if such a system is present, then we say the system is stable. Why? Because the output does not exist indefinitely after the input has been cut off. In this case, when sigma 0 was positive, what did we see? Our output is going on increasing. Not only is it not decreasing, it is actually going on increasing. Hence, this is unbounded response. Now, when your sigma 0 is negative, on the other hand, what do we see? The response drawing on the same axis. Let me use a different sheet of paper. When sigma 0 less than 0, response will be like this, and this is following this curve. Okay. So, what we observe here is that as time increases, the output will decay or go down, and for some very large time interval the output will be negligible. So, this is the characteristic of a stable or bounded system. So, what do we conclude from here then? That if poles on left half of S plane implies system is stable. On the other hand, if poles on right half of S plane implies unstable. Okay. And if system, and the third option is if poles on the imaginary axis implies system is oscillatory. Okay. So, what do we mean by oscillatory? So, we saw what happens when sigma 0 is positive and when sigma 0 is negative. Now, if suppose your sigma 0 is equal to 0, okay. If that is 0, then our V t will simply be equal to 2 cos of omega m t. So, the output response will be like this then. Okay. This type of system is called oscillatory. Okay. Now, one other issue that frequently comes up is how should the system behave depending on the number of poles that it has. I mean in the feedback system. So, so we saw how the closed loop system behaves when we have the open loop transfer function using the Nyquist plot in the frequency domain. But can we make such a similar analysis depending on how many poles the open loop transfer function has? So, while discussing the frequency domain response, we saw that if the number of circulations of the point -1 0 on the Nyquist plot was non-zero, then the system is unstable. Let us see whether we can make a similar analysis based on the number of poles that the open loop transfer function has. So, suppose your open loop transfer function so if your system has only one pole, then I can write my open loop transfer function like this. And this is of course of the type of a low pass filter with a single upper 3 dB frequency. Now, the feedback transfer function will be given by okay. So, then first thing we note that the bandwidth with the of the feedback system is given by this, and this we had seen while studying the effects of feedback, that bandwidth enhancement takes place, and the poles of this system will be where. So, omega p was the pole of the open loop system. So, this is our S plane, this is sigma, this is j omega. Initially, for the open loop system, the single pole of the open loop transfer function lied at minus omega p, okay. And so, this is minus omega p. Of course, the transfer function that we have chosen here, in this transfer function, the pole is on the left half of the S plane for stability. So, that is why we have this plus in the denominator and not a minus. So, the pole therefore lies at minus omega p, and after applying the feedback, what we see is the pole shifts leftwards, is not it? This is minus omega p, if I beg your pardon. So, the new pole of the closed loop transfer function is at minus omega p f, and this has a lower value, or it shifts much farther away from the imaginary axis j omega, which basically means that the stability of the system actually improves, because now this pole of the closed loop system is much farther away from the imaginary axis as compared to the pole of the open loop system. And we all know on a frequency graph how this looks. So, here these are of course the asymptotic plots. This is my A f0 or DC gain with feedback, this is A of f, this is A, the DC gain. So, my initial pole was at omega p, the new pole with feedback is at omega p f. So, what do we observe here? That on application of feedback, the pole can shift only in the negative sigma direction. So, what it means is that feedback, after applying feedback for a system with a single pole, under no circumstances can the system become unstable, okay, because even after feedback the pole is still lying on the left half of the S plane. Not only is it lying on the left half of the S plane, it is further away from the j omega axis. Hence, for a single pole system, feedback, even after feedback, of course here by feedback we mean negative feedback, the system continues to be stable. Hence, for a system whose open loop transfer function has a single pole is said to be unconditionally stable. Which means that whatever you do, the stability of the system cannot be altered. It will continue to remain stable even after feedback. So, in this module we covered the various types of response that we can expect depending on the location of the poles, that is in the left half of the S plane, the right half of the S plane, or on the imaginary axis. We also saw what the response will be for a single pole, and what we conclude is that for a system whose open loop transfer function contains just a single pole, such a system even after applying feedback will continue to remain stable, and any form of negative whatever form of negative feedback we apply for any frequency, it will retain its stability. Hence, such a system is said to be unconditionally stable. In the next module, we shall see what happens when we have more than one poles. Thank you.